Solutions to assignment questions. In this question, we can easily see that she is using her right hand. For this question, it is more difficult to see which hand she is using. So we look at the image, and then we can see this is her left hand, this is her right hand in the image. In this way, we may know she is using her left hand. The emblems have the laterally inverted characters in the font because we may let other drivers in the font to read the word ambulance normally on their rear mirrors. For this question, what you have to do is to follow the following steps. Number 1, locate and draw the image. Then, draw the virtual rays and reflected rays, one by one, like this. Lastly, draw the incident rays, and remember to draw the arrows to show their directions. What about the diagram on the right hand side? First, you have to find the image, mark it, and then draw the reflected ray and virtual rays. Reflected rays and virtual rays again. And lastly, finish with the incident rays. For this question, you have to draw the diagram to see how John may see Mary. John sees Mary because there is Mary's image produced by the mirror. So you should first of all draw Mary's image and then draw the virtual ray, reflected ray, and incident rays, one after another. This is for part A and B to show John sees Mary. What about part C? Mary sees John. You have to draw another diagram, and this time you have to draw John's image. Draw the virtual ray, reflected ray, and then finish it with the incident ray. For part D, John walks to the right. What happened to John's image? John's image also moves to the right. The speed is the same, in the same direction, to the right. There are 8 ray diagrams for you to complete. For all of them, follow the following steps. First of all, locate and draw the image. Then you may draw the virtual rays and reflected rays. Draw the incident rays to complete the diagram, and remember to draw arrows to show direction. Here is the first ray diagram. The image looks like this. On the right, at the same distance from the mirror as the object is. Then draw the virtual rays and reflected rays, one after another. And then the incident rays with arrows. And you may complete the diagram in this way. Or you may draw another set of rays from the tail of the object. And this is done. The next one looks like this, with inverted object. And of course the image is also inverted. First, you draw the virtual rays and reflected rays. And then the incident rays with arrows. You may draw another set from the tip of the object in this way. Next, you have an object pointing in this direction. So the image would be something like this. you may draw the virtual rays and reflected rays again from the tail of the image, and then they should start from the tail of the object. Similarly, you may draw another set for the tip of the object. Next comes a triangle, so the image would be also a triangle on the right, behind the mirror. You may draw rays, incident and reflected rays in this way, or you may draw another set from another vertex of the triangle. What about if the mirror is inclined in this direction? The image is there, and so you may draw the two sets of light rays in this direction. Next, the object is a boy, and so the image would also be a boy, laterally inverted, left side right. Similarly, you draw the virtual ray and reflected ray, and then finish it with the incident ray. To show that the boy can see his whole image, there should be another light ray from the head to his eye. So we start with a virtual ray, reflected ray, and that light ray comes from the head of the boy. In this way, we show that he can see his whole image by such a short length of mirror only. Next, we will a big rectangle, and so the image look like this. And you may draw the two sets of rays from one corner of the rectangle, and also another set from another. Here comes the last one. The image look like this, and you may draw two sets of light rays from two vertices of the triangle. And now let's draw the diagram again to show how this boy may see himself in the mirror. Again, we draw the virtual rays and reflected rays first, and then complete it with incident rays. We do it again for the head of the boy. And in this way, the diagram look like they are twins. And now the boy is looking at his brother outside a window. So how big the window should be to see the whole brother outside? To answer the question, we have to find a pair of similar triangles. And in this way, the length L and H are related by the length U and 2U. We may set up an equation which is L over U equals H over 2U. And in this way, we have found the minimum length of the mirror for the boy to see his whole image behind the mirror. And this length is half of his height. So if the boy moves closer or further away from the mirror, would the minimum length L changes? If they are closer or further away, we can see there's no change in the ratio because the ratio comes from the similar triangles. So the minimum length of mirror does not change. So what is the minimum length of mirror for this lady to see the whole image of herself? This is almost the same situation as in the last question. So the answer would be half of the height of the lady. So we know the minimum length of mirror for one to see the whole image of oneself. What about when mother wants to see Sam, or mother wants to see Mary? First of all, we have to draw the images of Mary and Sam. And after doing so, we have to find similar triangles as before. And now in order to find the minimum length x, we set up the equation. 3 over x equals 6 over 1.3. Similarly, for the case of Mary, we do the same steps. We find similar triangles, but you can see that the length ratio is a bit different. For y, it would be 3 over y equals 4.5 over 1.2. So solve these equations to find the values of x and y.
You have to do an experiment about the refraction of light in the next lesson. You will be given a semicircular perspex block, and light will be directed to the center of the block at different angles. You have to find the relationship between the angles. The angle of incidence is measured in air, the larger angle here, and the angle of refraction is measured in perspex, the smaller angle here. These two angles are related by a formula called Snell's law. You must bring along your calculator in order to find the relationship between the angles. So what is refraction? Refraction occurs when light travels across an interface. An interface is the area of contact between two different medium. For example, vacuum and glass. When light travels from vacuum to glass, the speed of the light changes, and in this way, the direction of the light also changes. The relationship between the angle of incidence and the angle of refraction is given by the Snell's law, which looks like this. By using Snell's law, you will be able to find the angle of refraction for a given medium, such as glass. So you will be given a semicircular block made of perspex, which is a kind of transparent plastic, just like glass. You have to use a ray box again and direct the light to the center of the semicircular block. And then you have to measure the angle of incidence and the corresponding angle of refraction. Fill in the result in the table here, and then you have to calculate the sign of the angles using the next table below. So make sure you bring along with your calculator. And then you have to plot a graph of sine I versus sine R, which means the vertical axis to be sine I, where I is the angle of incidence, and for the horizontal axis it is sine R, where R is the angle of refraction. Your graph will look like this, which means sine I is directly proportional to sine R. And the ratio between them is called refractive index. In this way, refractive index will then be equals to sine I over sine R. And you may find the value of refractive index directly from the slope of the graph. So you should find the refractive index of perspex from the graph directly. What you find will be close to something like 1.5, and for refractive index of other common media, they are listed below.